Hello, my dear students. Let's after this break, I will continue this chapters. I'm sorry. I will continue this chapter. We have a lot of information will come now, and I will need to cover with you. All of them based on that you already studied the equation of the plan and the equation of a straight line. So now for the summary of the previous session. For a straight line, you will have to have a vector in the direction of a straight line, and just only one point belongs to this straight line. For an equation of a plan, all you have to do, or you have to know, one point belongs to this plan, and a normal vector on this plan. So this is the information that you should know very well about a plan and straight line. Now we'll go through a bunch of information connecting the relation between straight line, plan, intersections, two straight lines in a space, two vectors, semi-like, and so on. Now for this equation, which is very simple, which summarizes how to get the distance between 2 points in 3D or in R3. If you have B and Q are 2 points in R3, we define the distance by the magnitude of the direction vector connecting these 2 points. So if I have these 2 points, P and Q, x1, y1, z1, x2, y2, z2, just to get the difference between the coordinates, x1 minus x2, y1 minus y2, z1 minus z2, then get the square root of the squares of these coordinates, the magnitude of this vector, which is going to be the distance, really very simple. Let f1 and f2 be points, lines or plans of R3. We define the distance connecting F1 and F2, either points, lines, whatever. It is the minimum of the set D of B and Q, such that P belongs to F1 and Q belongs to F2. So if you have two straight lines, if you have two plans, if you have 2 points, the shortest distance should be the distance connecting them should be the shortest distance between these 2 points. If the point belongs to the straight line, the plan, or whatever, get the minimum of the distance between these 2 points. It is a concept, and true. Every point in any space belongs to infinitely number of vector spaces. This is exactly true. So if you have 1, 2, 3, 1, 2, 3 as a point, you have infinite number of lines that's passing through this point, and also infinite number of plans passing through this point, plus all the quadratics that already exist in R3 can pass through this point. So this is really a very deep statement. Remark, if F1 intersection F2 doesn't equal to a phi, so if you have two plans, two straight lines, whatever, and their intersection doesn't equal to phi, then the distance F1, F2 equal to 0, which means if they are already intersected, so the distance between them will be 0. So if I have two intersected straight line, the distance between these two straight lines is going to be 0. If you have two intersecting plans, that's a plan and that's another plan, and they are intersecting, so the distance between them is going to equal to 0. That's what this statement about. A distance from a point and straight line. It's really very simple. All I have to do is to get the direction vector connecting the point that you need to find its distance and the point of formation of a straight line, cross the multiplication of u, which is the vector of this straight line, get the magnitude of this cross multiplication divided by the magnitude of u. So now if I have line R, which in line R you already know that this is the vector u, and you have A and P, which is the connection, which is the point on the straight line. So this is actually straight line R, which contains a point and a vector. It's exactly like what we said. This is the direction vector, and this a point belongs to R. And I need to find the distance between another point and this straight line. All I have to do, and of course the shortest distance is the perpendicular distance between both of them. The simplest thing to do is to get the vector of this straight line, which is given, u, and to get a direction vector between A and B, the difference between their coordinates, make a cross multiplication between these two vectors, get the magnitude, and divided by the magnitude of u, you will have the distance of this straight line. The proof already exists on the main slides. Okay, if I want to get a distance from a point to a plane, also it's really very simple. All I have to do is to get the inner product of an AB and the normal vector, divided by the magnitude of the normal vector. So that's the law that we are using if you want to find the distance between a point and a straight line, and that's the law that we are using once you are trying to get a distance between a point and a plane, which is really very simple. Okay, once more, this is point A, which is one of the points in the plane. This is point P, which is not belonging to this plane, but it already exists. I will get the vector connecting A and B, and then I will make a cross multiplication between this direction vector AB and the orthogonal or the normal vector of the plane. Multiplying them, I will get the inner product, take the modulus because you are talking about distance, so there is no meaning of a negative sign, and then divide by the magnitude of the A. So this is a short description for the angles and the trigonometry behind this law. But this is mainly the law that I would use for finding a distance between a point and a straight line, and this is how to find a distance between a point and a plane. Okay, lines in space, there is a lot of cases expressing the relation between lines in space. So if I have R1, that's a straight line, completely defined, so I know a point of the vector. And this is line 2, which is also completely defined, so I know its direction vector and the point. In space, in 3D, you will have this case, which states that these two lines either part of each other or equal each other, or actually they are the same line, or you will have this case which expresses the case of parallel to straight lines. You may also find two straight lines intersecting like this, and also you can find two straight lines on such a case, which they are skew straight lines. So actually, if we are talking about the cases of straight lines in space, we will have R1 equal to R2, which means that they are coinciding each other. So actually they are one line, they have same vector and sharing same points. And the second case, if they are strictly parallel, so this is R1 and that's R2, and we will see the condition. The third case is intersecting straight lines, they are intersecting each other. And the last case is about skew straight lines. The skew straight lines are two straight lines, they are not parallel to each other, they are not intersecting either. This one belongs to a plane, and that one belongs to another plane. Both these planes are parallel to each other, okay, because if they are not parallel, okay, if they are, just a second please, okay, so, it's not for sure to be parallel to each other, but they belongs to different planes, so these are the cases that you may find between two straight lines. Two skew straight lines. So I have four cases, as I told you. They are coincided in each other, they are parallel, intersecting, or simply they are skewed. So how to differentiate between these cases? If I said these straight lines are given, so you already know a point, at least on each one of them, and a direction vector, so you already can form its equation. So if I say that R1 will have a vector U1, R2 will have a vector U2, and the point E1, I will say it belongs to R1. So the blue line is R1, and the point A belongs to it. In the first two cases, A and B, okay, they have the same direction. So either they are coincides on each other, they will have the same direction, or if they are parallel, so they will have also the same direction. So if they have the same direction, which means U1 to U2 are, they have the same ratio in coordinates, which means that if U1, let's say A1, A2, A3, U2, B1, B2, and B3, you will find A1 on B1 equal to A2 on B2 equal to A3 on B3, which means that U1 is parallel to U2. So they are sharing the same ratio, as I told you. So this is the condition for these 2 points. How to differentiate between these 2 straight lines? The points here on R1 are exactly the same the points on R2. But here, the points on R1 are different than the points of R2. So once more, in order not to forget, these 2 lines are parallel. So all the set of points belongs to R1. They are different than the set of points belongs to R2. If they coincide on each other, if they are like this, the points will be the same. So if I want to check, these 2 direction vectors will have a ratio. How to differentiate between case A and case B? Here the point A1, which belongs to R1, will belong also to R2. So this is the first case. But in the second case, A1 doesn't belong to R2. And it will be written now. A1 belongs to R2, and A1 doesn't belong to R2. A1 stands once more for the point that's already exists in R1. Make complete sense. So, for the cases of C and D, both of these 2 cases, U1 and U2 don't have the same direction, which means that A1 on B1 doesn't equal to A2 B2 or doesn't equal to A3 B3. Actually, any not equality of these, either all of them or at least one of them, it means they are not parallel to each other. How to differentiate between them? Here you will find R1 and the intersection R2 doesn't equal to phi, which means there is a point shared between both of them. And this is really very easy to find. All I have to do is to get one of these straight lines on its parametric form, x, y, and z, and try to take this information about x, y, and z with in parametric form, and the substitute just only in 2 ratios of R2, you will get the t. Make a back substitution, you will get the intersection point. So, but for here, their intersection, it's not equal to phi, it means they intersect. But here in this case, their intersection equal to phi, which means they are not intersecting. They are belongs to a different, completely, 2 different planes. This is what's all in this slide. It's really very important slide. You should go through it more than once. Okay, for the distances, if we want to interpret from all of these situations or cases between the straight lines, I can also express them as distances. So in this case, the distance will equal to 0 because they already coincide on each other. These 2 straight lines are actually one line, so there is no distance between them. Okay, if they are parallel, so the distance between these 2 straight lines will be the distance between a point on one of them and the other straight line, exactly like the distance we took previously between a point and the straight line. So all I have to do is to find the point from this line and use the distance law that we did go through it previously in the previous slides and apply it on the second line. You will get the distance connecting them. So once more, the distance R1, R2, and the distance of any point on R1 to the line R2 or vice versa, it will be the same. Okay, in case of C, which they are intersecting, also the distance will equal to 0. But if they are skew straight lines, all I have to do is to get a point from the straight line and get the equation of the plan and they get a distance between this point and the plan. So actually, in this case, I'm using the distance between two straight lines, or between a point and the straight line to be the specific. And in that case, I will use the law which find the distance between a point and a plan. Point belongs to the straight line and the plan. Okay, so it's perfectly, it's really very perfect. It's very simple. So once more, if I want to get the distance between these two skew straight lines, all I have to do is to get the equation of this plan. I should have it. And I know the equation of this straight line, so I know a point. Get the distance between a point and the plan, and you will find the distance between these two straight lines. It's really very simple. Now, relative position of a line and a plan. If I have a line and we have a plan, like the plan of this whiteboard. So the cases are the following. Either this straight line belongs to this plan. So this is case number one. Or this line is parallel to this plan. Or this line intersect this plan. So now, once more, if this stands before a plan, and this is my straight line, I will have this case, which indicates that this straight line coincides or contained or a subset from this plan. Or this case, which means that this straight line is parallel to this plan, and also it's very, very easy to prove. The third case is a straight line intersecting with a plan, and also it's really simple. So once more, here's R as a subset of B. So R, it's already fall within the plan that we are talking about. Here we can say that this straight line is parallel to that plan. So they are parallel to each other. These two cases share the fact that the normal vector of this plan is perpendicular on this straight line. Exactly like this case. The normal vector of this plan is also perpendicular on this straight line. So either you have a straight line belongs to a plan, you will find the normal vector perpendicular to it, or if you have a line which is parallel to a plan, also in a similar manner, you will find the direction ratio of the line is perpendicular on the, or orthogonal on the normal vector of your plan. Okay, the last case is you have a straight line and intersecting the plan in one point, and we already did go through something like this once we had the equation of a straight line, putting it into a parametric form, then making the substitution, getting the value of t and resub in the parametric equation of the straight line to get the intersection point. So, how to differentiate once more? If we say that u is the direction vector of this straight line, omega or w, which is the vector perpendicular to this plan, point A point belongs to R. So, in the first case, I will have the normal vector, which is perpendicular. So, W times U, or the inner product of the orthogonal complement times the vector of this straight line will equal to 0. But in the last one, they are not going to equal to 0. In this case, they are not going to be equal. Okay, once more, they are not going to be equal to each other. So if I get the ratio of the vector of the straight line, the direction vector, and the normal vector of the plan, their inner product equal to 0, so it will be the cases either A or B. But if the inner product doesn't equal to 0, it means this straight line will cut this plan. Okay, perfect. How to differentiate between cases A and B? To differentiate between case A and B, all the blocks that belongs to R already are points belongs to the plan. So if I have the point belongs to R, which is A1, it will satisfy the equation of the plan. But in this case, the normal vector is perpendicular or orthogonal on the direction vector of the straight line, but they are not sharing the points. The points that already exist on this straight line doesn't belong to this plan, and this is stated in here that A doesn't belong to your plan. Okay, it's really very simple and also very important slide. So now you have the slides that using the laws in it, which indicates the distance between a point and a straight line, a point and the plan. You have the different 4 cases of straight lines in 3 dimensions, and also you have the cases of straight line and a plan. Okay, perfect. This problem is really very important, or it has a lot of ideas behind it. I will solve it with you, and also I will solve it also using a different method or another solution with the slides. Here is stating to you, let O such that E1, E2, E3 be an orthogonal set. So now I have E1, E2, E3, which is basis for R3. They are the standard, which is IJK. This is 1, 0, 0, 1, 0, 0, 0, 1, or any other orthogonal set. And positively oriented, and we know that the positively oriented set, okay, it's exactly IJK. So let R be the line defined about the following normal equation. I'm giving you this straight line equation. And this straight line equation, if you look exactly to it, it means I'm giving you a point and a vector. I'm giving you a point and a vector, a point and a vector. I'm giving you these 2 information. Number 1, x equal to 2, so all the points belongs to this straight line, which share the fact that their x coordinate equal to 2. And y minus 3 over 2 equals z over 4. In another way, write all of this, I can say that the point that belongs to this straight line is simply, this is the point that belongs to this straight line, which is 2 and then 3 and 0. Because this equation can be simply put on the form x minus 2 over 1 equal to y minus 3 over 2 equal to z minus 0 over 4. So the point that we are talking about is 2, 3, and 0, and the vector is 1, 2, 4. And we can also find the vector in plenty of ways. So now I know a point for fact, which is 2, 3, 0, and we also know the vector of this straight line. I can find also any point belongs to this straight line, which is really very simple. So if I need another point, let's say A, which is gonna be sharing the x point 2, okay? And for how to find the y and the z components for another point. So actually the line equation or the set for this vector, it's x minus 2 over 0, I'm sorry, and y minus 0 over 2, z minus 0 over 4. To make it easier for you and to be on the form, to avoid having 0 as a vector in the symmetric equation, I will tell you the explanation, which is really very simple. Let's get another point. So I will put x equal to 2 and I will choose any value for y. Let's say I will consider the point with y coordinate equal to 1. All I have to do is to use this ratio. Inserting here y equal to 1. So 1 minus 3 is going to be negative 2. Negative 2 over 2 is going to be negative 1. Get the value of z, which is negative 4. These, for example, 2 points now belongs to the straight line, which is R. Of course, I can get infinite number of points belongs to this straight line. If I want to get the vector of this straight line now, it's going to be really very easy, which is 2 minus 2 equal to 0. 1 minus 3 is going to be negative 3. Negative 4 minus 0, which is going to be negative 4. I can use it this way or write it 3, 0, 3, and 4. Between us, also, I can, from a blank here, write it like this. X minus 2 over 0, but people feel not comfortable about writing this equation on this form. This is going to be y minus 3 over 2, and this is going to be z minus 0 over a 4. But as I told you, 1 minus 3 is going to be a negative 2, as I told you. So these are the vectors, as we said. So I want to get to use directly the point that exists on this straight line, which is 2, 3, and 0. Here we go. And use another point. Let's say that I will consider x equal to 2, stand for the first coordinate. Let y equal to 1, any point from your mind, any number. And make a substitution in this ratio to get the value, the corresponding or the compensating value of z. So 1 minus 3 is going to be negative 2 over 2 negative 1. Then make a cross multiplication, you will have z equal to negative 4. Subtract them from each other to get the direction vector, which is going to be 0, 1 minus 3, negative 2, and negative 4. This is actually what's preferred for this case. Also, you already know that I can rewrite on the symmetric form, but we have a lot, we don't prefer to write it this way to avoid the idea of dividing over 0, but it's not a division. Actually, it's a ratio, so it's 1 minus 2, also the same vector goes in the denominator. Okay, so this is what's stated, or this is the advantage of knowing the information about straight line. Also, he make it clear for you that we are going to use a plan. So if I want to make this like that, this is my straight line R, and which has the direction vector, which is 0, negative 2, and a negative over 4. This is 0, negative 2, and the negative 4. And I have 2 points. I will use the given point, which is 2, 3, and 0. So now I have a point and a vector. For the plan, for the plan equation, I have the plan, and I have 3 points belongs to this plan. So it's 1, 0, and the negative 1. And this is for an A. And also we have B, which is 2, 2, and 0. And also we have C, which is 1, 1, and 1. Now also I can find the equation of this plan. And in order to find this, or to do this equation, or to write it, it's really very simple. Also from these 2 points, or the point and the direction vector, I can write the parametric equation of this straight line if I like. And also from here, I can write the equation of the plan, but I would need it, so I will do it. How to get the equation of the plan knowing 3 points? It's really very simple. All I have to do is to you have 2 ways, either to form the determinants that I told you about, or to make a cross multiplication of these 2 vectors, or direction vectors belongs to this plan, in order to get the normal vector. Then write the equation of the plan based on knowing the normal vector and one of these points. Let's do the normal vector idea. Okay, now I can simply make a cross multiplication between the 2 direction ratios that belongs to the 2 direction vectors that belongs to the plan P. So this is direction ratio number 1, cross direction ratio number 2, and this will give me the normal vector of this plan. So I will go for 2 minus 1. This is I and J and K, or you can write E1, E2, E3, it will make no difference. So I will go for IJK or E1, E2, E3, it's really up to you. Then I will start. 2 minus 1, 2 minus 1, it's going to be 1. This is for the direction vector number 1. 2 minus 0, which is 2. 0 minus of a negative 1, so it's going to be positive 1. So once more, 2 minus 1 is going to be 1. 2 minus 0 is going to be 2. 0 minus of a negative 1 is going to be positive 1. Exactly in a similar manner, I will do either AB, BC, or CA, it's up to you. I will use this one. 1 minus 1, so it's going to come up to 0. 1 minus 0, so it's going to be 1. And 1 minus negative 1, so it's going to be a 2. Now I have 2 vectors, 2 direction vectors, belongs to this plan. I'm making a cross product in order to get their normal vector. So simply, once more, 2 minus 1. 2 minus 0, 0 minus negative 1 is going to be a positive. Same way like 1 minus 1 is going to be a 0, 1 minus 0 is going to be a 1, 1 minus of a negative 1, which is going to come up to 2. Now I can find the normal vector of B. So this is the orthogonal complement or the normal vector of B, which is simply can be written as the following. So actually, now I'm getting this normal vector, okay, which is, let's say, normal vector of P. How to do it? I will get to I, erasing the row and column. So 2 times 2, which is going to be 4, minus 1, so the first component is going to be 3. Then for the second component, it's going to be a negative, erasing row and column, so it's going to be 1 times 2, also 1 times 0, 0, so to make no difference. For the last component, it's going to be 1 times 1, which is going to be a 1. So this is actually the normal vector of this plan. So the equation of this plan can be written as the following. 3 of an x, negative 2 of a y, plus a z minus, open a bracket, equal to 0. All I have to do is to get the multiplication of these coordinates times any of these points. I will use point number C, for example. So 3 times 1 is going to be a 3. Negative 2 times 1, which is going to be a negative 2. 1 times 1, which is going to be a plus of a 1. So once more, 3 times 1, negative 2 times 1, 1 times 1 equal to 1. And now the P equation is 3 of x minus 2 of y plus a z. Then I will have 3 minus 2, so it's going to be 1 plus 1, so it's going to be negative 2 equal to 0, and that's the equation of the line. So let's do it once more and see what he needs. He's telling me that you have a frame of reference, which is E1, E2, and E3, or RJK. Okay, now we know our frame of reference. He gave me a straight line, so I went ahead knowing that giving a straight line means you know a vector and a point. I have now my point and I have my vector. So actually in analytic geometry, you have all the knowledge through not just only chapter 8, but also with the previous chapters. All of them are in your mind. The idea is, what are you going to use to do what? So now I've taken advantage from the straight line, knowing the line, the point and the vector. So this is what we can get from the straight line equation, if we want to form it. And from the plan equation, the given information, now I have a normal vector. This is for the plan equation part. I can have, now I know the normal vector plus a point belongs to this plan. Okay, giving you the straight line and the plan. What we want to see is to show that R strictly parallel to B. So if I want to see that the straight line R actually is parallel to the plan P. How to do it? If I want to do this, I will have to get two points, actually. First of all, in order to have a strictly parallel, it means that the normal vector of your plan should be perpendicular on the direction ratio or orthogonal on the direction ratio of your straight line. And this is easily can be done by the following. This is the normal vector of P. So if this is R and that's its direction vector, and this is the normal vector of this plan, this is our normal vector. So if they are parallel, then their inner product should equal to 0. So all I have to do is to get the direction vector of R, okay, and making an inner product with P, and let's see what's gonna be. The direction vector of R, which is 0, negative 2, and negative of a 4, and I will do an inner product with the normal vector of this plan, which is 3, okay, 3, negative 2, and 1. Let's see. 0 times 3 plus negative 2 times negative 2, so negative 2 times negative 2, and then plus 1 times negative of a 4, so you will have 0 plus a 4 minus 4, which equal to 0. That indicates that the normal vector, this is the normal vector of V, that's the normal vector of the plan, is orthogonal on the direction vector of R. So the first condition is already correct. So now I'm sure that the direction vector of this plan, okay, the normal vector of this plan is perpendicular on the direction ratio of the straight line. In order to be sure that they are strictly parallel, all I have to do is to take a point from the straight line and to show that it doesn't belong to the equation of the plan. How to do it? I will simply make us see if this point, one of these points of the straight line, belongs to this plan. How to be sure about this? If it satisfies its equation. So all I have to do is to get the equation of the plan, which is simply 3 of an x, negative 2 of a y, plus a z minus 2 equal to 0, which is the equation of the plan. And I will take the point from the straight line. I will choose 2, 3, and 0. Let's see if this point belongs to this plan. How to see that? Simply substitute. So it's going to be 3 times 2 minus 2 times 3 minus plus replace z by its value, which is 0, minus 2 equal to, let's see, 3 times 2, which is going to be a 6, negative 2 times 3, which is going to be a negative 6, plus a 0 minus 2, which means it doesn't equal to 0, which means they are not sharing same points. So this straight line is parallel to this plan.